Okay, so I'm going to be going through rocks and weathering. There are 3 sections to this topic. There are tectonic plates, weathering, and mass movement. I'll be going through all of these sections one by one. I'll start with tectonic plates. I'll be going through the cross section of the Earth, why tectonic plates move, plate boundaries, what these plate boundaries create, and of course I will include examples. Okay, so here we have the cross section of the Earth. The cross section of the Earth is split into 4 parts. These are the inner core, outer core, mantle, and the crust. The crust is about 100 kilometers thick at its thickest point. It is the Earth's outermost layer. So right here is the crust. This whole section here, the brownish gray section, is all the crust. It is made of solid rock and is relatively thin in comparison to the other sections of the Earth. It is divided into 2 types. There's the oceanic crust and the continental crust. So the oceanic crust is just what's underneath the ocean, and then the continental crust is what we know as continents, or it's just the on land. It's just the part of the crust that's on land. I will dive into these a little bit later when we talk about tectonic plates. So then we get to the mantle. So the mantle lies between the outer core and the crust. It is mainly made up of solid rock, but this solid rock can flow over long periods of time due to high temperature and pressure. So the mantle is mainly solid, however, it does flow. It doesn't make much sense, but you can think of it as being solid here towards the outer core, and then it becomes more liquidy as we approach the crust. And then below the crust, all of this rock here is turned into magma, and this magma is a liquid and it moves around. Okay, so that's the mantle. It's about 2,900 kilometers deep. Okay, now we get to the outer core. Change color. Here's the outer core. The outer core is located beneath the mantle and extends to about 5,100 kilometers deep. It is made of liquid iron and nickel. So it is liquid. This mantle is both solid and liquid, mainly solid towards the bottom, mainly liquid towards the top. However, the outer core is liquid, and this is what generates the Earth's magnetic field through a geodynamo process, but we don't need to know about that. And then here's the inner core, right at the center of the Earth. It's the innermost layer of the Earth and is about 6,300 kilometers deep. It is composed of solid iron and nickel, so the inner core is solid. And it is solid because of the immense pressure acting down of it. So all of this weight and gravity acts onto this inner core. Yeah. Spotted. And then this whole section here is under the greatest pressure, and it is extremely hot. Yeah, that's about it for the cross section of the Earth. So now what's next? So why tectonic plates move? Okay, here we go. Here's just a quick picture. It's quite bad, but you get the gist of it. So tectonic plates move because the mantle, the section underneath the crust, is constantly moving. So just below the crust, there is constant movement because the magma below it is moving. Okay, so now we get to plate boundaries. So I will start with divergent plate boundaries. So a divergent plate boundary is when there are two tectonic plates and these tectonic plates move away from each other. Okay, so you can think of divergent plate boundaries as divorced plate boundaries. So when people get divorced, they want to be away from each other. So they move away from each other. Okay, so this movement results in the formation of new crust as magma rises from the mantle and solidifies at the boundary. So let's say this is an oceanic divergent plate boundary. These are also known as oceanic constructive. So let's say that these are two oceanic plates moving away from each other. They will form an, where is it? Let me just copy. They will form an, come on, an oceanic constructive plate boundary. So what happens here is magma from the mantle will come up. Let me use orange. Will come up and fill this gap. Okay, so underwater, magma will come up, fill this gap, and create an mid-ocean ridge. So an example of this is the mid-Atlantic ridge, where two oceanic plates move away from each other. So there is a divergent plate boundary underwater, mid-ocean ridge, and these create underwater mountain ranges. So this magma flows up between the plate boundaries and it will solidify and create a ridge. Okay, and then as these plate boundaries separate, they can also create volcanic activity. Okay, unlike oceanic constructive plate boundaries, let's draw it over here, we are going to make a continental constructive plate boundary. So here I'm going to make continental constructive plate boundary. So what happens here is the plates also move away from each other. However, because the crust is very thick here, because it's continental, because the crust is very thick, there will be no magma coming up to fill this gap, and a valley will be created. So an example of this is the East African Rift Valley, which is separating at a rate of 2 centimeters per year. Okay, so that's it for divergent plate boundaries. Now we come to convergent plate boundaries. Okay, so convergent plate boundaries occur when two plates come together. So divergent, you could think of divorced plate boundaries. They want to go away from each other. Convergent, you could think of coming together. So the plates want to come together. They want to be with each other. So at convergent plate boundaries, tectonic plates move towards each other and collide. There are three types of these boundaries. So we get oceanic let's see if I can paste this, not sure if it'll work. So we get oceanic continental convergence. These occur when an oceanic plate collides with a continental plate, and this will result in, so let me draw it here. Oh, wrong thing. How can I do it? There we go. Okay, let me draw it here. So this will result in a denser oceanic plate being forced beneath the continental plate. So at a oceanic continental convergence, we have the, let me do the oceanic plate in dark. We have the oceanic plate moving below the continental plate, like so. This process is called subduction. So this process here is called subduction. And this can lead to the formation of deep oceanic trenches, volcanic arcs, and seismic activity, so earthquakes. Yeah. So an example of this is there's the Juan de Fuca and the North American plate boundary. Probably butchered that name, but I'll see if I can find a photo of it. No, not really. I don't know, but that's not really a good example. Okay, but I think the Andes is an example of an oceanic continental convergence. Let me just make sure. Okay, yeah. So an example of an oceanic continental convergence is the Andes Mountain in South America. So here we go. It's a bit rough, but now you can kind of see it. So here we have, let me make it smaller. You can zoom in. Okay. So here we have the oceanic. Here we have the oceanic plate. Here we have the continental plate. They come together and form the Andes mountain range. Yeah. So that is oceanic continental convergence. Now let's move on to oceanic convergence. Okay. So oceanic convergence. So this occurs when two oceanic plates collide and the denser of the two oceanic plates subducts beneath the other. This results in the formation of deep trenches and volcanic island arcs. An example of this are the Japanese islands. So it's very similar to this. However, you can replace the continental plate with an oceanic plate. Okay, so now let me just show that. I'll show this here. Okay, here we go. So you see here is a continental crust and an oceanic crust coming together. They create land as Japan, and here's Pacific plate, an oceanic, and here's the Philippine Sea plate, also an oceanic plate. Pacific is heavier than the Philippine Sea plate, so it will subduct underneath. Yeah, so it also but it also forms islands. And then it will also form volcanic activity. Okay, And then finally we get continental convergence. So continental convergence. This is when two continental plates collide and neither subducts because they have similar densities. Instead, they crumple and create vast mountain ranges like the Himalayas. So right here, we have where's the brush? We have continental, they come together, and because they both have similar densities, they end up pushing against each other, like so. Pushing against each other like so. And this forms mountain ranges like the Himalayas. There is not that much volcanic activity around continental convergences. This is because the crust is very thick. And then finally we get transform plate boundaries. So here we go. So transform plate boundaries. So transform plate boundaries occur when two tectonic plates, so let's say this is one big plate, this is another big plate, slide past each other horizontally in opposite directions. So this plate's moving this way, this plate's moving this way, and then they slide past each other. This movement results in a lot of friction and can cause earthquakes along these fault lines. So along here, earthquakes occur. An example of a transform plate boundary is the San Andreas Fault in California. Okay, and that brings us to the end, I think it's the end of, where is it? That brings us to the end of plate boundaries. Now let's go through what these plate boundaries create. Okay, so let's start with the, where's the text? Let's start with divergent plate boundaries. So divergent plate boundaries create mid-oceanic ridges. This is an undersea mountain range that is created as tectonic plates move apart, with magma rising and solidifying along the boundary. So here we have, here we have oceanic plates. They are moving away from each other, and this gap in between that is created is filled by magma, and it creates a mountain range as it solidifies. So this hot rock becomes solid and creates mountain ranges. Divergent plate boundaries can cause ocean basins. This is the gap left behind if this does not occur. So when the ridges are not formed, ocean basins are formed, which basically just means they move apart and then the magma does not shoot up, it just fills in this gap underneath here without shooting up. And then they also cause volcanic activity. This is because the magma comes up and then creates volcanoes. And then they create earthquakes because as they pull apart, they can get stuck and cause jolts, which causes earthquakes. Okay, that's it. Oh yeah, and then these are both oceanic. Continental divergence will cause a rift valley. So this can be seen in the African Rift Valley. Yeah, the Horn of Africa. Okay, now we get to convergent plate boundaries. Let me just move along this way. So now we get to convergent plate boundaries. So let's start with the oceanic continental boundaries. So start with oceanic continental. Okay, so remember convergent means they're coming together. So these boundaries or tectonic plates that come together. So here we have the subduction zone, oceanic underneath continental. This will create a deep ocean trench as seen here. This will be, let me use blue, this will be a deep trench, and it will create volcanic arcs and earthquakes. And there will also be somewhat of a mountain range here. An example of an oceanic continental convergence is the Andes Mountains. Okay, now we get to oceanic convergence. So this is very similar to the oceanic continental. The heavier plate will subduct underneath the lighter plate, and it will also form island arcs, which is just like, here's the top of the water because this is underwater. So island arcs will form. So here's an island, this right here is an island, and then trenches will also form. So oceanic and oceanic continental are basically the same thing, and they create the same thing. However, continental convergence. Okay, let me just make sure I get this different color. Continental convergence results in both plates being squashed together. So both plates are being squashed together, and then this will form vast mountain ranges such as the Himalayas. So think of Mount Everest as the tallest mountain on Earth, and then just remember that it is formed at a continental plate boundary. And then, yeah, convergent plate boundaries cause volcanic activity, and they cause earthquakes. And now we get to transformative plate boundaries, or transform plate boundaries. Okay, so these occur when two plates move along each other. So one plate moves this way, one plate moves this way. They create fault lines, which is just, here's one plate, here's another plate. Fault line is just the area where these two plates meet. And they create earthquakes because while they are moving, they can get stuck, which causes a jolt, which causes an earthquake. And unlike the convergent and the divergent plate boundaries, there is no creation or destruction of the crust. Okay, moving on. We are finished with tectonic plates. Let's move on to weathering. So physical types of weathering. Okay, so first we need to understand what weathering is. So weathering is essentially just the breakdown of rocks. There are a few different ways rocks are broken down, and I will start by going through the physical processes that break down rocks. I think there are 5 different types. Okay, so let's start with freeze-thaw. So freeze-thaw occurs in cold areas where ice forms as water freezes in the cracks of rocks. Okay, so here we have, it's gonna be a bit rough, but here we have a rock with a crack. Okay, so this crack will fill with water, and then when it gets cold, this water will expand because ice expands about 110% the size of water. So when water freezes, it expands, and this will exert, if you want statistics, an average of 14 kilograms per centimeter squared. So let's just 14 kilograms per centimeter squared of pressure. Okay, so as this freeze thaw process continues, there is a constant pressure acting on this rock, and this rock will be wedged open by ice, and it will eventually cut through the rock. Yeah, so that's freeze thaw. Freeze thaw is basically cold temperature. Water gets into a rock. When this water freezes, it expands, which forces the rock open and will eventually crack the rock, causing weathering. Moving on, we get to, let me make this one in red, we get to exfoliation. So exfoliation occurs mainly in hot deserts with large diurnal energy range. So exfoliation occurs when there is a large temperature change throughout the day. So for instance, in a desert, it can be up to, say, 40 degrees Celsius during the day. However, at night, this temperature can drop to below zero. So it can drop to below 0 degrees Celsius. This means that the rocks will expand and will contract because of temperature. So when it is 40 degrees Celsius, the rock will expand, and at night, let me draw an arrow, at night, because it gets cooler, this rock will then contract back to a smaller size. So the outer layer of the rock will contract. Okay, so this creates stresses within the outer layers of the rock, and eventually these stresses will create cracking and flaking of these rocks. So if you are ever in a desert, just look at the rocks around you, especially the dark ones, like the black rocks. They will often have chips on them, or they will have rock chips lying around them. Okay, now we get to the next type, which is, let me put it over here, salt crystal growth. So salt crystal growth occurs because of salt water entering cracks in rocks. The salt water will eventually evaporate, just leaving salt crystals. And when these rocks get heated, these salt crystals, let me do the crystals in a light blue, these salt crystals expand, exerting pressure on the rock, and eventually this rock will crack all the way open because of salt. Salt crystal growth is most effective in climates that reach 27 degrees Celsius, and salt can be expected to increase by 300% at this temperature. Okay, that's about it. Now we get to dilation. This is not very common. However, it does occur. If you get asked about different physical processes, I would advise you against using this as an example, because it is quite complicated, because it relies on a number of factors such as glacier load and removal by erosion. It's quite complex, so rather just don't understand this. If you get asked this, unlucky, but I doubt they'll ask this because it's a very complex type of erosion. But basically it occurs because when there's a glacier on top of rocks. On top of rocks, these rocks are compressed, and then when this glacier melts, these rocks are exposed, and because they're under less pressure, they will expand. And this can cause fractures in the rocks because of the quick expansion rate. However, it also occurs in cliff faces. So here's a cliff, there are rocks in this cliff, and because they are under a lot of pressure, they can split and crack. Yeah. And then finally we get to please copy. And then finally we get to vegetation root action. So vegetation root action is just when there is, let me just draw another tree. Okay, so there's a tree. When this tree's roots, there's a big root, there's another big root, there's another big root. When these trees' roots grow into a rock, like into the cracks of a rock, they will expand over time. So as this tree grows, the size of its roots will also expand, and this will force the rock to crack. Okay, that's about it for physical. Moving on to chemical weathering. Okay, so chemical weathering, we have three main types. The first one being hydrolysis. So hydrolysis is when acidic or alkaline water reacts with rocks and breaks them down. So we have water. So this water has a pH level. So water is normally at a pH level of 7. We can just make it easy. 7 pH is normal water pH level. So for hydrolysis to take place, the water pH level has to either be way below 7 or way above 7. Okay. An example of hydrolysis is when acidic water reacts with feldspar in granite to form kaolin and salicylic acid and potassium hydroxyl. Okay, so first type of chemical weathering is hydrolysis. Okay, second type is hydration. Do this light blue. Second type is hydration. So hydration occurs when certain minerals in rocks absorb water. This allows these minerals to expand, and it causes stress within the rock. So let me make this rock. So here's a rock. Water reacts with this rock, so there's water drips onto this rock. Minerals inside of this rock collect this water or absorb this moisture, and these minerals then expand in size, creating internal stresses on the rock, which will eventually cause the rock to crack. Okay, and then finally we have carbonation. So carbonation occurs mainly when acid rain breaks down limestone or chalk. So carbonation occurs when we have acid rain. So it rains, acid rain, remember that, acid rain. It rains onto rocks such as limestone, and then this limestone will dissolve. It will basically dissolve. Acid rain occurs when carbon dioxide dissolves into rainwater. Yeah, that's about it. That's about it for carbonation. Factors affecting weathering. Okay, so this is quite straightforward. So where's my cursor? There we go. Okay, so let's say an area has a high temp high temperature and a lot of water, so lots of water. Okay, this area will likely receive chemical weathering. Okay, so high average temperature and lots of water will result in chemical weathering. Okay, so now when there is a high temperature change and when there is, where's the brush? When there is not a lot of water, so then we will see exfoliation. And then finally, when there is a lot of temperature change, so high temperature change, come on, when there is a high temperature change and there is a lot of water, so there is a lot of water, this will result in frost wedging, or what I called it earlier, this will result in, well, how I said earlier, this frost wedging is the same as freeze thaw. Okay, so freeze thaw, frost wedging. Okay, so when there's a high temperature change and a lot of water in an area, we will experience frost wedging or freeze thaw. When there is a lot of temperature change and not a lot of water, we will experience exfoliation. And then when there is a lot of temperature, when there's a high temperature and a lot of water, you will experience chemical weathering. Okay, so those are the main factors you need to know for the factors influencing weathering. Okay, and now this brings us to mass movements. Oh yeah, and then examples. So here with chemical weathering, an example could be in Florida, where they receive a lot of rainfall and they receive a high average temperature. So chemical weathering occurs in Florida. When there is a lot of temperature change and not a lot of water, and exfoliation occurs. This can occur in any desert around the world. So you could use Egypt as an example, or you could use the Namib Desert, or you could use the Sahara Desert as an example of a lot of temperature change and not a lot of water. And then a lot of temperature change and a lot of water causes frost wedging or the freeze thaw. An example of this can be anywhere where it snows. So anywhere where the temperature reaches below 0 degrees Celsius. I would use Alaska as an example of freeze thaw. Yeah, that's about it. Okay, now finally we are moving on to mass movements. So how are mass movements categorized? I'm not going to go into detail with this because it's pretty straightforward. If you want to understand how mass movements are categorized, just look at this table here. Yeah. So as you can see, slowest is creep and the quickest is a river. Just look at this table and you should understand exactly how they're categorized. Okay. Now let's move on to the types of mass movement. Okay, so the first mass movement we're going to look at is a rockfall. So rockfalls occur when individual rocks or rock fragments break loose from a steep slope or cliff and free fall to the cliff's base. So they often happen due to freeze-thaw cycles or seismic activity and weathering. They occur at random. However, they are more likely to occur after heavy rainfall or a lot of snowmelt. Let me just quickly draw a rockfall. So here we have a mountain. Here we have a mountain. This is how the dark brown part is what the mountain looked like before the rockfall. Okay, so as you can see, right here, these rocks are unstable, and in a blink of an eye, they will break off the mountain and fall down to the bottom of the mountain. Okay, this happens because they become unstable and I think it's cohesive, and the cohesive forces and frictional forces that keep them up, that keep them here, are not strong enough to act against the force of gravity, which results in a rockfall. Okay, next we have a rock slide. Okay, so rock slide. So a rock slide involves the rapid downslope movement of a mass of bedrock along a well-defined sliding plane. This type of mass movement can be triggered by heavy rainfall, earthquakes, or volcanic eruptions. Okay, so rock slides are very similar to rock falls. However, they are not as steep as rock falls, so the slope that they are on is not as steep. However, the same rules apply, and the rocks will, instead of fall, they will just slide down the mountain until they reach the bottom and rest. Okay, moving on. Moving on to debris flow. Debris flow are fast-moving mixtures of water, soil, rock, and organic material. They typically occur in steep mountainous terrain and are often triggered by heavy rainfall, snowmelt, or volcanic eruptions. Debris flows can be highly destructive and can carry large boulders and trees downstream. So a debris flow is similar to rockfall and rockslide in the sense that it is just it's just earth falling down a hill. However, now a debris flow is mainly caused by water. So a debris flow occurs when there is a lot of moisture on the surface of this cliff or hill, which has saturated the soil. This makes the soil unsteady, meaning that the frictional forces and cohesive forces are not as strong, and this will cause a debris flow, which basically means the side of the mountain will just slide off and it will end up at the bottom. Yeah, that's about it. Then we get to mud flows. Okay. Now we get to mud flows. So mud flows are similar to debris flows, but they consist primarily of water and fine-grained sediment, such as clay and silt. Mud flows often occur in areas with loose soil and are frequently triggered by heavy rainfall, snowmelt, or a rapid melting glacier. So just think of mud flow. So a mud flow is just debris flow with more water. Okay, so more water in a debris flow, you'll get a mud flow. Less water in a mud flow, you'll get a debris flow. Okay, Now let's move on. Okay, landslides. So landslides are a general term for a downslope movement of mass of rock, soil, or debris. They can be triggered by various factors including heavy precipitation, rapid snowmelt, earthquakes, volcanic eruptions, human activities such as construction or mining, and changes in groundwater levels. Landslides can range from slow, gradual movements to rapid catastrophic events. So, in theory, a landslide a landslide is just a mass movement down a slope. So all of these will classify as a landslide. Because a landslide is just the general term for earth falling down a hill. That's all a landslide is. Okay. Now you get to the slower types of mass movements. Okay. Now we get to creeps, soil creep. So soil creep is a slow and continuous downslope movement of soil. It occurs due to the expansion and contraction of soil particles in response to temperature changes and the influence of gravity. Over time, this movement can lead to the tilting of structures and features on a hilltop. Okay, so soil creep is just it's very, very slow, and it is the movement of soil down a hill. Okay, so let me find a picture of it. Here is a picture of what soil creep looks like. Okay. So as you can see, when soil creep occurs, the trees are bent because the tree compensates for the movement. So the trunk of the tree will grow straight up, whereas the root system is being pulled down. Okay, so that's what soil creep is. That should be all the mass movements you need to know for geography. The others will never be asked in exams because they are too complex and they are localized forms of mass movement. Now let's move on to the effects of water on mass movements. Okay, so water. So water. So water increases the weight of a slope. Okay, so water adds weight to the soil and rock on slopes. This extra weight can make the materials more unstable and prone to sliding or collapsing downslope. So water increases the weight, which increases the likelihood of a mass movement. Okay, next up, water acts as lubrication. So water acts as lubrication between soils and rock particles. It reduces the friction that holds them in place, making it easier for them to move downslope. Water causes saturation. So when soil and rock become saturated with water, their cohesion and the strength decrease. This can lead to increased instability and the potential for mass movements like landslides and mudslides. So saturation is when there is a lot of water in the soil. Okay, next up we have erosion. So flowing water can erode the base of slopes, further weakening them. This erosion can undercut the stability of the slope, triggering mass movements. So let's say we have let me refer back to one of the earlier topics. So let's say we have a meander in a river. Okay. Here we have what's it called now? Here we have the river cliff. And as you can see, here we have undercutting. This undercutting is because of erosion that is caused by water flowing in the river. So when this erosion undercuts the cliff enough, it will cause this overhang here to break off and fall, which is a type of mass movement. And then finally, water causes freezing and thawing. So when water seeps into the cracks of rocks, it can freeze and expand during cold weather. This exerts pressure on the rock, and when this ice melts and it thaws, the forces within the rock are weakened, and this can contribute to the rock cracking and a rockfall occurring. So that should be it for the impact of water on mass movements. Now we have human impact on mass movement. Okay, let me try and fit it in here. So human activities can have a significant impact on mass movements, like landslides and erosion. The first reason for this is deforestation. Let me change the color. I'll change the color to green. Okay, first reason for this is deforestation. So when trees and vegetation are removed from slopes, the roots that once held the soil together are gone. This makes the soil more prone to erosion and landslides. So trees grow in the ground. So let me just draw a quick diagram. So here's a tree. Here's a slope. Here are the trees and roots. Tree, roots, tree, roots. Okay, let me make them a little bit green. Okay, so what happens is when these trees are cut down, there is nothing keeping this topsoil in place. So when there are heavy rains, there is no interception either. So when there are heavy rains, the water infiltrates straight into the ground, and this causes the soil to become saturated, and this can lead to a landslide or mudslide. Okay. Next up, we have construction and mining. So excavation for construction or mining can alter the natural slope of the land. Okay. This can disturb the balance of forces that holds the soil and rock in place, increasing the risk of mass movement. So let's say we had a mountain or we had a slope, went like this. Now we've decided to start mining it. So now the slope looks like this. Okay. Clearly, this area right here will be prone to mass movement. This is because there are less cohesive forces keeping this ground steady, and the frictional forces have been disturbed. Okay. The vibrations from the mining can also cause landslides and rockslides to take place, as these rocks are suddenly jolted out of place. Next up, we have building roads, road building. So roads often cut into hillsides. These alter the natural drainage patterns and increase the potential for erosion and landslides. So if a road is poorly constructed, it can increase these problems. So just think building a road is similar to the construction of mining in the sense that it interrupts the drainage and changes the natural state of the slope. Then we have urbanization. So urban development can lead to changes in land and let me repeat. Urbanization can, what am I saying now? Urban development can lead to changes in land and drainage patterns. As a result, more water can be channeled to slopes, increasing the risk of landslides and erosion. So urbanization, let's use the slope right here. So you decide to build a few houses on the slope. Okay, you decide to build a few houses on the slope. Okay, now there is more weight on the slope, and the drainage and the natural state of the slope have been altered. So this can cause mass movements as frictional forces have been disrupted, cohesive forces have been disrupted, and there is less drainage. Okay. What else is there? We have irrigation and water management. Okay. So irrigation and water management. Improper irrigation and water management can lead to saturated soil. This makes the soil more susceptible to erosion, and mismanaged water drainage systems can also contribute to mass movements. So let's say a hill is watered constantly, the same thing will happen as if it rained a lot on that hill. And because naturally it wouldn't have rained that much on that hill, the ground will become saturated and a mass movement process can occur. Okay. Now finally we get to the end of mass movements, and the last topic in mass movements is how mass movements can be reduced. Okay. Let me just do it here. Okay. So mass movements like landslides and erosion can be reduced by quite a few methods. The first one being as simple as planting trees and vegetation. Okay, planting trees and vegetation on slopes helps stabilize the soil. This happens because the tree's roots dig into the soil, locking the soil in place. Okay, the trees also act as interception when it rains, so this reduces the rate at which infiltration can occur. Okay, we can avoid deforestation by avoiding to cut down trees on slopes. We can make sure that the tree's roots continue to hold up the soil in these hilly areas. So protecting forests can prevent erosion and mass movements. Okay. Adding proper drainage. We can ensure that water drainage systems are well designed and maintained to prevent excessive water buildup on slopes. This reduces the risk of landslides. Terracing. On steep slopes, we can build terraces or steps to reduce the slope's angle. This can help prevent soil and rocks from moving downwards. So terracing is literally just changing the mountain so that the mountain looks like this. Okay, easy enough. We can build retaining walls. So these retaining walls will support and stabilize slopes. They can stop soil and prevent soil from sliding. So here we have the wall, and then the soil will be pushing against this wall like this, like so. Okay, and then the wall will stop it from going any further. Of course, we then have land use planning. Then we have, oh, come on, man, land use planning. So we can carefully plan the development around hilly areas to avoid disturbing steep slopes and critical areas prone to mass movements. So instead of building on a hill, we can build around the hill. So here's a hill. Instead of building a house on the hill, we can build houses around the bottom of the hill. This puts less stress on the slope and reduces the likelihood of a mass movement. We can monitor what's happening on the slope. So by implementing monitoring systems, we can keep an eye on the slope stability and take action if warning signs of mass movement are detected. So let's say we're monitoring the slope and we can see that the soil is saturated. We can evacuate people from below the slope, or we can open up a drainage system of some sort to reduce the likelihood of a mass movement. And then, of course, like most things, education and awareness. So by educating communities about the risks of mass movement and the importance of responsible land use practices, we can reduce the effect of mass movements. This brings us to the end of this topic. In the description of this video, I will add an essay that I wrote as an example for how to answer a question. My teacher gave me quite a good mark for this essay, so hopefully you can learn one or two things from this that answer the question. Yeah. Okay. This is the essay. If you would like to read through it and get some examples, or use the Chapman's Peak drive as a case study, please read the essay and you should do well. Okay, good luck.